to pay. Forgive and everything that we said when we were drunk. It doesn't matter 'cause it all came from love. Can't be too late. Been missing everything that we had. I miss you, babe. I miss you, babe.
Good morning, everyone. How you doing on this fine Monday? Well, we're back after a week of Easter break. And I hope you got refreshed and ready to tackle these last, what do we got? 4 weeks left? This is week 12, I think. Or maybe this is week 13, I don't remember. Anyway, so we have, if this is week 12, then we got 12, 13, 14, 15, 16. We got 5 weeks left to finish out the semester. That'll take us to about May 20th or something like that. And then that last week, we won't have any sessions. So we really got just 4 weeks left. So good morning, Serhi, Dorian, Motaba, Max, and anyone who's watching on YouTube, which includes Michael. We're going to spend the rest of the semester talking about graphs, but we're starting to transition ourselves away from the sort of run-of-the-mill graphs like I showed you the last time with shortest path and minimal spanning tree. Starting to work towards more specialized graphs, in particular ones that are used for compiling programs, transforming them from one programming language into another language, and also in doing regular expressions and pattern matching. So we've got a discussion about trees today. We're going to start looking at state machines, and then when we come back on Wednesday, we'll really dive into state machines and all their variations. And that'll take us through the rest of the semester. That'll take us through about the next 3 weeks or so, 3 or 4 weeks. And then we got about a week towards the end of the semester where I really kind of have nothing on the schedule. I put those days in there to act as the buffer days, so that if there's a day when like I'm unable to make the class, then I can move the whole schedule back by a couple of days. And then that would fill up those times. But we haven't had to do that this semester. So we do have a couple of days towards the end where we can talk about other things.
Are we going to have any additional assignments for graphs?
Yes, there will be 2. There is one coming up on regular expressions. That'll be another, almost like a programming assignment, although you won't do any Python programming. You'll be writing regular expressions. And then there will be another assignment based upon the finite state machines that we're doing, transforming finite state machines, and that'll be the last one. So there's really only, I think, 2 more assignments coming up.
Are those 2 topics related to graphs?
Yes, because they're kinds of graphs.
I didn't know that.
They have nodes and edges. They're just specialized kinds. Any other questions? Okay. Well, like I said, I wanted to start transitioning ourselves toward a discussion of how compilers work. And this is going to be acting as a kind of a vehicle towards the rest of the topics for the semester. Now, if you've taken some of my other classes, you might have already seen this illustration that I'm about to draw. But basically, a compiler is just a program that reads in a file as input and then transforms that file into some other kind of output and then writes that file to disk. That's basically all a compiler does. And anytime you write a program, you've taken 1, 2, maybe 3 semesters of programming, anytime you write a program that does essentially that, it pulls in a file, does something to that file, then outputs a new file, we're kind of like training you to get this idea of what a compiler does. I mean, right now, your assignments maybe read in a file that consists of some text, and then maybe do something like capitalize all the letters, or take out the punctuation or something like that. But you're doing a transformation to the text, and then outputting the results to another file. That's basically what a compiler does. It's a little more complicated. So a modern compiler actually takes your source code and transforms it in several different ways, with the final result being that target language that you're going for, which may be the actual ones and zeros, the binary code for the processor that you're running it on, or it could be some other language. There are, compilers don't have to compile down to machine code. They can compile to other languages. For example, there are Java to JavaScript compilers that allow you to write a Java program, transform it into JavaScript, and then run it on a web browser. And you probably already know that Java itself is compiled not to the native ones and zeros, the machine code for the processor. In fact, it's just compiled for a virtual machine. And so it's compiled to the ones and zeros for that virtual machine, and then another program takes over to transform those ones and zeros into the native ones and zeros. So really, most programming languages aren't really just starting with your source code and going all the way down to the native ones and zeros. They go through a series of steps, and whether all those steps take place up front during the explicit compilation phase, or whether they take place some up front and some later on, it doesn't matter. But eventually, your source code gets transformed into some other programming language. So let's draw this diagram here. So you start with your source code, which could be C or Java or Python. And then the source code goes through the first step, which is known by a variety of names. It's either called a scanner, or a lexer, or a tokenizer. It's kind of 3 names for the same thing. And let's say that the source code that you're compiling is, and again, it doesn't have to be a real programming language like C or C++. It can be something that you made up. And let's say this programming language is really simple. All it does is allows you to do variable assignment and execution of expressions. So let's say it's something like x equals 3 times y plus 6. So let's say that's the source code that you put in. So the job of the scanner or lexer or tokenizer is to go through that source code and identify all of the parts and give each one of those parts a name. Kind of like going through a sentence in English or French or whatever and identifying all of the parts of speech. Like this is a noun, this is a verb, this is an article, this is an adverb. So that's what the tokenizer does. It goes through your program and kind of marks each one of the pieces with what that thing is. And what comes out the other end is called a token stream. So it's taken this source code, x equals 3 times y plus 6, and then it's basically tagged each one of these pieces with what that thing is. This x over here, which we might call a variable, in compiler speak is called an identifier. It's a name for something. And then this 3 right here, that's a number. In particular, it's an integer. And depending upon your programming language, there may be a distinction between integers and floating point numbers. Or it could be there's no distinction. It's just a number. Then this y here, that's an identifier also. The 6 is an integer. And then those other symbols, like this equal sign here, that's the assignment operator. Operators, again, compiler speak, operators are basically symbols or operations that kind of sit in the middle and then usually have operands, like 3 plus 4, the operator is the plus, and the 3 and the 4 are the operands, the things the operator operates on. And then the asterisk is the multiplication operator. The plus is the addition operator. And then even the semicolon on the end usually has a name. Just call it semicolon because it doesn't really have any other name. But that's the token stream there. It's taken my source code there and marked each one of the pieces. It's split it up basically into a series of tokens. Each one of those tokens has a name and it's got a value. So the name might be like integer and the value is 3. Or the name might be multiplication operator. Or the name might be identifier and the value is x or y. Okay, so that token stream comes out, and then it goes into the next phase. And this is called the parser. The parser's job is to take the token stream and then rearrange it into a data structure called an abstract syntax tree. So the abstract syntax tree takes the program code and hierarchically organizes it so that at the bottom of the tree you've got the tokens, and then towards the top of the tree you have the, how to describe this, like the combination of the tokens that finally produces the entire program. Let me draw what the abstract syntax tree might look like for this particular statement. The other thing the abstract syntax tree also encompasses is the order of operations. So towards the bottom of the tree are the first operations you do, and towards the top of the tree are the last operations you do. So if you look at this statement here, the first operation we would do is we would multiply 3 and y together. And by the way, when you do an assignment, you always execute or evaluate the right-hand side, and then you do the left-hand side, which means the equals is basically the last thing you do, the actual assignment. So we've got the 3 and the y, and both of those have been tagged as integers and identifiers. And then we combine those together and do multiplication. This is the multiplication operator. Then we got the 6, which is combined together with the plus operator. This is an integer. And then the add operator. And then finally, these are joined together with the x. This is an identifier. And this is the assignment. So that's what the abstract syntax tree looks like. That's what the parser does. So the parser really does two things. First of all, it organizes the program into an abstract syntax tree. And if it is successful in doing so, it means that the program you have fed into this compiler obeys the rules of the language. It's kind of like the grammar of the language. So the rules of the language might say things like, if you are going to multiply things together, there must be something to the left and to the right of the multiply sign. Or if you're going to do an assignment, there must be a variable, an identifier, sitting off to the left-hand side, and an expression off to the right-hand side. For example, the rules might say, this is illegal, 3 equals x. We can't do that in this particular language. There are probably actually some programming languages in which that's legal to do. But in this one, it's not legal to do. So the grammar, the rules of the language, will state that when you do an assignment, there has to be an identifier off to the left and an expression off to the right, and anything else is not allowed. I'll show you towards the end of today what those grammar rules look like. So the final thing is to notice that in this abstract syntax tree, we've also embodied the order of operations. We've got 3 and y multiplied together, and then that comes up and adds that to the result of that to the 6, and then the result of that addition gets assigned to x. And so you can build an abstract syntax tree out of an entire program that includes loops and conditionals and assignments and functions. You build one giant syntax tree out of that entire program. And if you're successful, if the parser is successful in doing so, it means that the program is grammatically correct. Okay, what the parser doesn't do at this point is evaluate whether the program makes sense. You know, that's for another phase, which I'm going to show you next. The abstract syntax tree then goes into the next phase, which is called semantic analysis. Semantic is a fancy word that means what something means. So the semantic analysis goes through and it makes sure that the program makes sense. It applies additional rules to your program. And these rules are ones about like the order that things happen in. For example, your programming language may require you to declare a variable before you use it. And so semantic analysis will make sure that that happens. The parser doesn't deal with that. The parser is only concerned with, do the individual statements in the program make sense? Do they obey the rules of the language? But the parser doesn't do things like the order of the statements. Another thing about semantic analysis would be make sure that when I do an assignment, I'm matching up the types correctly. Like if I have x, which is declared to be an integer, and I have a string, hello. I can't assign the string to X because my particular language disallows that sort of assignment. So the semantic analysis asks the question and verifies, does the program make sense? So it's basically just a yes, no. Does it make sense or not? So the abstract syntax tree comes out of semantic analysis and it goes into code generation. And this is where the final transformation is made from basically the source code into the target language. The code generator might produce assembly language as its output. It might produce another programming language like JavaScript as its output. It might produce something else entirely. But code generation goes through the abstract syntax tree, basically walks through the tree, looking at each one of the nodes in the tree. And for every single one of those nodes, it outputs some piece of code in your target language. And then most compilers will go through one additional phase called the optimizer. The optimizer's job is to take that target language and clean it up. Now, for example, if you just output assembly language for every single statement in the program, you'll probably find that there are some redundant, unnecessary things that get outputted just because you're walking through the tree and outputting code as you see it. For example, you might put the results of a calculation into a register, and then the next calculation pulls the results out of that register and then puts the results of the next operation into another register. So you didn't really need to put the results of the first operation in the register and then pull it back out again. You could have just skipped it entirely. Actually, let me back up. I said that incorrectly. You take the results of a calculation and put it into memory because it goes into a variable, and then you take the contents of that variable and pull it back out into a register. So you didn't really need to put it in a memory just to pull it back out again. You could eliminate those two statements and clean up the code a bit. Or you can do what's called like dead code elimination. If you've got an if-else condition and the compiler determines that the if is always going to be true, then you can eliminate the else section entirely. Or there's a function that doesn't get called anywhere. It gets declared, it gets defined, code is generated for it, but then it turns out it's never called anywhere. So you can just eliminate that out of your program. So these are all things that the code optimizer does to kind of clean up the resulting target language, make it more compact, and make it run faster. So that's basically how a modern compiler works these days. It starts with your source code, sends it through the lexer, and then the parser, then the semantic analysis, code generation, optimization, and each one of those boxes is probably going to be a program by itself. So there's one program for doing the tokenizing, and then there's another program for doing the parsing, and another program for doing the code generation, another one for doing the semantic analysis. It's not just one big giant program. Oh, and I guess how you spell optimizer depends upon where you live. I guess here in the United States we spell it with a Z, and in other parts of the world it's spelled with an S. But it's basically the same thing. So I hope, if you haven't already, at some point in a college or university degree program, you do end up taking a course in compiler construction, because I think it's really kind of a big eye-opener. It takes all the stuff that you've been learning, data structures, how to read and write files, and how to transform data from one form into another, and it puts that all together to produce this program that just reads in a file which consists of source code and outputs another file which consists of more source code in another language. For me personally, it was a two semester sequence. The first semester we just focused entirely on writing the lexer. That was it. That's all we did, is getting it through that first box. And then the second semester we did the rest of it up through code generation. So by the end of the year, we had this compiler that could take a small programming language. You know, it wasn't a huge language like Java or C or anything like that. It was a very compact, small, simple language for just doing educational purposes, and took it up through code generation. Now the code it produced was horrible and slow and bloated, but it worked. And then when I went on to my graduate studies, my master's program, that's when we did that final box, the code, the optimizer box. And so we learned how to take the code generated by that compiler we wrote in our undergraduate and then clean up the code and learn about ways to optimize the code, like reduce the number of registers being used and dead code elimination and evaluating constants at compile time, things like that. And I really think that was kind of one of those aha moments in my education when I went from, oh, there's this magical thing called a compiler that we type programs into and it makes them run, to, wow, I really kind of understand how this stuff all works. And compilers aren't really mysterious anymore. They're just computer programs that people wrote. And sometimes they have bugs in them. We hope that they don't have too many bugs in them, but sometimes they have bugs in them, and it's people like you and I who make compilers better and better, especially that last box, that optimizer box, is where a lot of the research in compilers goes on today, in getting the code to run faster and faster. So, any questions about that? So in the compiler phase, there was this thing called the abstract syntax tree, that it takes the source code of your program, which is written in a linear style, right? It's basically just, although it looks to us like it's two-dimensional text, it's really just one long line of text with some carriage return characters in the middle of it. But it takes that essentially one-dimensional string of text and it turns it into a two-dimensional data structure called an abstract syntax tree, which is just a specialized kind of tree. So I wanted to take a few minutes to talk more about trees because they're really important in computer science and in computer programming. So as you know, trees have a root, which is usually up at the top. It's got leaves, which are down at the bottom. And trees are also a graph that is acyclic, which means that it's always like you go from the top down towards the bottom. There's no loops in the tree that would make you go in circles. There's no connection between a node at the bottom towards one at the top. So in tree terminology, you've got the root at the top, you've got nodes, which are each one of these circles, and then leaves are just the nodes that are at the bottom that don't have anything below them. So a node is really just a data structure that holds a value, like the value of an integer or the name of a variable, and then it has children below it. And in the case of a binary tree, it has two children, one that goes to the left and one that goes to the right. So a binary tree is a specialized kind of tree where each node has just two children, or I should say at most two children. It could have 0, it could have 1, but and it has at most 2. The tree that I've shown you up here at the top is not a binary tree because there's a node here that has 3 children. That can happen in an abstract syntax tree, but I want to focus on binary trees for just a moment. Oh, the question is, how do loops work if they're acyclic? So the abstract syntax tree is not a picture of the execution of the program. It's a picture of the structure of the program. When the code is generated, and you have something like a loop embodied in there, then you'll generate code that causes the looping to happen. So when you get to the bottom of, when you get to that closing brace of a loop, then you'll output a piece of code that basically says jump back up to the top of the loop. And then the execution of the program will have a loop. But the structure of the program, the way the program is written, doesn't itself have any loops in it. So again, the abstract syntax tree does not embody the execution of the program. It embodies how the program is written. Okay, so a node has a value, and it's got a left child and a right child in the case of a binary tree. And the cool thing about binary trees is that it can be used to organize some data that you put into it. Now, for example, if I put in, let's say, I don't know, names of fruit into a binary tree, I start with an empty tree, and then I put in, let's say, I'll put in mango. Okay, so I put in mango as my first one here. And then another fruit might be orange. So I could put orange below that. And let's say I could put cherry here. And strawberry. I'm not putting these really in any particular order, but I am organizing them into a structure. Now, if you're thinking, why am I not putting them in kind of alphabetical order? That's actually a different kind of binary tree. That's called a binary search tree, in which they're organized into alphabetical order. But here I'm not doing that, and I'm doing that for a reason. So I'm just simply putting fruits into this tree and just organizing it from top to bottom. Okay, so here's my binary tree. Each node has at most 2 children. That's what makes it binary. But it's not a binary search tree because the nodes are not organized in alphabetical order. So once you have your data organized in a tree, you can then do these traversals of the tree. And I think I've talked about traversals before, but we'll go over them a little bit more here. So you can do what's called a pre-order traversal. And here's how a pre-order traversal works. So you start at the root of the node. And first you descend left. So at each node, you do these 3 steps. You descend left, then you output the value that you find there. And then you descend right. Okay? That's how you do a pre-order traversal. So let's work through this. So you do these 3 steps at every single node. So you start here at mango. And the first thing you're going to do is descend left. So you're going to go this way, and you're going to find your way at orange. So orange is a new node. So now you do those 3 steps. You descend left. So you go to strawberry, and then you do those 3 steps. You descend left, but there's no left to do. So then you go to the next step, which is output the value. Okay, you following along? So the first thing you're going to output is strawberry. And then you do the 3rd step, which is descend right. Remember, you're still at strawberry here. And there's no right to do, so now you're done with that node. Now you remember where we left off? the last node that we did was orange. So we had just finished step number 1 of orange, and now we're ready to do step number 2 of orange, which is output its value. And then we do step number 3 of orange, which is descend right. So we go down here to apple, and now we're at a new node, so we start the process over again. We're going to descend left, go down to peach. At peach, we're going to descend left. Well, there is no left, so we'll then move to the next step, which is output the value. And then descend right. But there's no right, so now we're done with peach. And we go back up to apple. Remember, for apple, we had only done step number 1. So now we do step number 2, which is output the value. And then descend right. But there is no right, so then we're done with apple, and we go back up to orange. Remember, orange, we had descended right. So now we're done with orange, and we go back up to mango. Now, mango, we had only completed step number 1. We still have to do steps number 2 and 3. So step 2 is to output the value. Oh, I just realized I apologize here. I just realized that these are not the instructions for a pre-order traversal. These are the instructions for an in-order traversal. So I'm just going to change that one thing right there. Okay, where do we leave off? So we did mango. We did step number 1 for mango. We are now going to output its value and then do step number 3. So step number 3 is to descend right. We come to cherry. Step number 1 for cherry is descend left. Step number 1 for watermelon is descend left, but there's nothing to the left. So then we output its value, which is watermelon. Then we attempt to descend right, and there's no right. So now we're done with watermelon, and we come back up to cherry. With cherry, we had only done step number 1, so now we're going to do step number 2, which is output its value. Then we'll do step number 3, which is to descend right, and that takes us to grape. With grape, we'll do number 1, descend left. Well, there is no left. We'll then output its value. And then we'll attempt to go right. There's no right, so we'll go back up to cherry. We're done with cherry. We go to mango. We're done with mango. And now we're finished. And this is the order of the nodes that we will output as we're doing an in-order traversal. Okay, now let's do a pre-order traversal, the one that I meant to do first. Sorry, I'm not writing very clearly today. I'm out of practice of writing. So a pre-order traversal, we're going to output value. Then we'll descend left. Then we'll descend right. So notice you still have 3 steps. It's just that the outputting the value is now first instead of second. Okay, so we start at the top. For mango, we do step number 1 first, which is the output the value. And then we head off to the left. And then we come to orange. Orange's first step is to output the value. And then we descend left. And we come to strawberry. And the first thing to do there is output its value. And then at strawberry, we're going to try to descend left. There's nothing there. We'll try to go right. There's nothing there. So we're done with strawberry, and we go back up to orange. Now with orange, we had done outputting the value, and we had descended left. The next thing is to descend right. So what's going to be the next thing that we output? We're going to go to orange. We're going to follow it to the right. What's going to be the next value that we output? I gotcha. You've been following along and just listening, and now I've asked you a question. So we were at orange. We descended right. What would be the next thing we output? Will it be apple or peach? Good. It'll be apple. Very good, because we come down here to apple. The first step is to output its value. And then we descend left, which takes us to peach. Peach's first step is to output its value. Then we try to go left, nothing there. Try to go right, nothing there. We come back up to apple, try to go right, nothing there. So we come back up to orange. We're done with orange. And with mango, oops, we're not quite done with it, but we have output its value. We did go to the left, and now we go to the right. So the next one is cherry, and then watermelon, and then grape. Okay, so that's a pre-order traversal. So the difference between a pre-order traversal and an in-order traversal is with a pre-order, you output the value first, and with an in-order traversal, you output the value in the middle. So there's one final traversal called a post-order. And you can probably guess what the order of operations are. It's descend left, descend right, and then finally output the value. So can you guess, or can you calculate what the output will be? So the question is there no go up in the algorithm? There doesn't have to be explicitly one, because when you descend left, you are just recursively calling the same function. So you have a function called like evaluate node. And then if you're doing a pre-order traversal, the instructions will be output the value, so it'll be like a print statement, and then a call to evaluate node. And you just pass in as its parameter the node that you're going to, the left child in this case, and then a call to evaluate node, and you pass in the right child. And then the process just starts all over again. And so when you're done with your 3 steps, you'll return out of that function call or that procedure call, and that will take you back to where you were before. So this is a recursive data structure. Every node has children below it. And so you can just call the same function over and over again, and it will automatically go through the tree, descend through it, and then return yourself back up to the top. And that leads us to the question, like, what happens if you have a really huge tree? Is it safe to use this algorithm? You know, I'd say so. Most call stacks can accommodate, 1,000 recursive calls or more, or you can actually pass into your programming language if you think the tree is going to be taller than 1,000 levels deep, which I would guess most are not taller than that. Then you can tell it, I want to make a larger call stack. And some programming languages, compilers, when they detect that you are doing recursive calls, will automatically make the call stack bigger so that you can do these things. So I think a lot of people are always worried about, like, what if the call stack is too small for my recursion? That doesn't happen in practice, really. In practice, that doesn't happen. It's only like in these extreme cases where you have to worry about that sort of thing. Okay, so if we're doing a post-order traversal, what's the output going to be? What's the very first thing it's going to output? We're starting up here at mango. We're going to go left, then go right, then output the value. So what will be the first thing it outputs? No, it's not peach. It's not grape. So we'll start here at mango, we'll go left, then at orange, we'll go left, and at strawberry, we'll go left, there's nothing there. We'll try to go right, there's nothing there, and then finally we'll output the value. So strawberry is the first thing. Which one is next? What comes next after strawberry? And while you're thinking about that, yeah, so if you know that you're going to be doing really deep recursion, you can always just make your own stack and do it that way. Okay, peach is next, because after strawberry, we try to go right, there's nothing there. So we return back up to orange, and then orange's next step is to go right. Apple's first step is to go left. Peach will try to go left, and then go right, and then finally it'll output itself. What comes after peach? Apple, good. And then after apple, how about this? What are the next three after apple? Just put in the chat, what are the next three? all your chats are all jumbled up. Can you put the next three like in one chat? It's like it's this, this, and this. All right, a couple of you got it. It's orange, watermelon, grape. So after we're done with apple, we come back up to orange. Orange's last step is to output itself. So we got orange. Then we come up to mango and then go right. At cherry, we go left. At watermelon, there's no left and no right, so we output itself. Then we come back up to cherry, go down to grape. Grape tries to go left and right, nothing there. So then we do grape. So it's, what did I say? Orange, watermelon, and then grape. And then the last two are then cherry and mango. Okay, so that's a pre-order traversal, an in-order traversal, and a post-order traversal. What does this have to do with programming languages? Let me show you. So we've got that expression that we were working with a couple slides ago, and we had turned that into an abstract syntax tree, which looks like this. Now, if we do a pre-order traversal of this, what do we get? So we start here at the equals, we go left. Whoops, for a pre-order traversal, remember we output the value first. So the first thing that comes out is equals. Then we go to the left, and the first thing we output there is x. And then there's no left and right. So we're done with the equal and the x, and then we go back up to the top, and now we head down to the right-hand side. Then we get plus times 3y, and then 6. So that's what you get if you do a pre-order traversal of this abstract syntax tree. How about if you do an in-order? Well, if you do an in-order traversal, you're going to get x equals 3 times y plus 6. You get back the same thing that you started with. And how about if you do a post order? With a post order traversal, you get back x 3 y times 6 plus equals. So you get back the same tokens, but just in different orders. Now, what's the difference between these? Well, it kind of depends upon what your target language is. If you are targeting assembly language or a what's called a stack-based architecture, and in fact, the Java virtual machine is a stack-based architecture, then the post-order traversal is probably the one you want to do. Turns out that the order of the tokens here almost directly reflects the actual order that you would do things in assembly language. In the same language, you would do something like load x into register 1. So take the value out of memory location x and put it in register 1. Then you would load the number 3 and put it into register 2. And then load the value of y and put it into register 3. Multiply registers 2 and 3 together. And put the result in the register 4. This is all assuming that there's an infinite number of registers. The optimization step will go through and reduce the number of registers. And I showed you how to do that a couple weeks ago. And then we would load 6 into register 5. Add registers 4 and 5 together, put the results into register 6, and then finally store register 6 into register 1. Sorry, the writing got kind of squeezed down there at the bottom, but basically you just walk through that post-order traversal, and every time you encounter a token, you emit one or more lines of assembly code, and that basically becomes your program to evaluate this expression. So post-order traversals are great for assembly language output. Also happens to be the input for this Hewlett-Packard calculator. If I was evaluating that expression, I would input it basically from left to right, and it would evaluate that by pushing the results onto a stack. In fact, that's how this Hewlett-Packard calculator works. Let me show you. If I was to take let's do a simple expression here, like 3 times 2 plus 6. The way I evaluate that on this calculator is I would do 3, see if we can see this here. Focus, focus. There we go. I would do 3, and then 2. Oops, I typed in too many 3s there. Let's try that again. 3, 2, and then I hit multiply, and then I do 6, and then plus, and that gives me the answer. So I have to move, in this calculator, I have to move all of the operations after the things that I want to operate on. So instead of typing 3 plus 2, I type in 3, 2 plus. So here's the keys that I typed in. I typed in 3, 2 times 6 plus. So in my head, I transformed the infix expression in which the operand comes in between the operators come in between the operands. I transformed it in my head into what's called a postfix expression in which the operators come after the operands. It's pretty easy to do once you get used to it. And so the way the calculator evaluated this is it pushed 3 onto the stack, and then it pushed 2 onto that. Then when I hit the multiply key, it takes the top 2 values on the stack, multiplies them together, and then pushes the result onto the stack. So this became 6, and then I type in another 6, and that gets pushed on, and then I do plus, and then it takes the top 2 off, adds them together, and then pushes the result back on, and I get 12. If I wanted to do something like 10 plus 5 times 3, then the way I would type that into the calculator is I would do 10, 5, 3 times plus. So the way that would work is it would push 10 onto the stack, then 10, 5, 10, 5, 3. I'm just showing the stack growing and shrinking from left to right here. Then I do multiply. So it takes the top 2 off, multiplies them together, and pushes the result. And then I do add. It takes the top 2 off, adds them together, and then pushes the result. And I get 25. So I'll do that here. Get this to focus. There we go. So I go 10, 5, 3. Okay. Now the stack here on this calculator is drawn upside down, but so it pushes from the bottom and pops from the top, from the bottom. But then I do, what is it? What's next? Multiply, and then finally add, and I get 25 as my answer. So the advantage of these calculators is, if you look around, you'll see there's no parentheses anywhere here. So the order of operations is done by just going left to right through my expression. You know, to be honest, I kind of wish that, I mean, the whole reason we have these order of operations is like purely historic, right? They've been around for hundreds, if not thousands of years, and we just learned over time that things like multiplication and division come first, and then addition and subtraction come later. There's no like fundamental reason why that has to be that way. We could have decided to do addition and subtraction first and the multiplication later. There's no like mathematical reason why it has to be the way that it is. And so we have to put in things like parentheses in order to change the order of operations, so that if we want addition to be done first, we put parentheses around that so that we end up doing that one first instead of the multiplication. But again, it's actually easier to teach kids, just go left to right. You know, if you want to teach, there's actually a programming language out there called Scratch. Not Scratch, I'm thinking Squeak, not Scratch, Squeak. And in that programming language, the expressions are evaluated strictly from left to right. You don't have to worry about parentheses, you just go left to right. And so there's no order of operations. The only order of operations is simply whichever one comes first, like, you know, from left to right. And so it's easy to teach kids the Squeak programming language because you don't have to teach them about, you know, multiplication comes first and then addition. You can teach this to, you know, 5-year-olds and 6-year-olds who don't yet have the mathematical maturity to be able to evaluate order of operations. You just say it just goes left to right. And it's easy to do. And there's no reason why multiplication has to come first. It's just a convention that we've developed over hundreds of years. So anyway, so back to this drawing here. What about the in-order traversal? Well, that would be good for transforming one programming language into a similar programming language. So if you want to transform, let's say, Java into JavaScript, which has a very similar structure, and they both use the same kind of operations, then in-order traversal would be probably the one you want to do. And what about a pre-order traversal? That one just looks weird. But if I was to turn each one of those operators into a function call, it actually might not look so weird. Let's turn the equals into a let. The plus into add. The multiply symbol into mult. And throw in a few parentheses, and then it looks like this. It looks like just a series of function calls. And then since you always do the innermost set of parentheses first, you're going to do the multiplication first. And then the result of that becomes the first parameter to the add, along with the 6. And then the result of that becomes the second parameter to this let. And if you're familiar with programming languages like Lisp or Scheme, they just put the parentheses in a slightly different place. It looks like this. Define x plus times 3y 6, close, close. So pre-order traversals do have their purposes also, and if you want to target a programming language in which are usually called functional languages, in which functions come first and are the primary way of organizing your program code, then a pre-order traversal works great. So the type of traversal you do is going to depend upon what your target language is. If you're targeting assembly language, do a post-order traversal. If you're targeting another language that is similar to the one that you are coming from, then in-order works great. And if you're targeting a language in which you call functions or you want to put the operators first, then you do a pre-order traversal. They're all variations on what's called a depth-first traversal. Notice that we always descend first, right? We always try to go down as far as we can. In a breadth-first traversal, you would kind of arrange the tree in layers. And you do like the first layer first, then the whole second layer, then the whole third layer, then the whole fourth layer as you're going down through the tree. That doesn't make so much sense from a programming language point of view. Okay, so that's abstract syntax trees in a nutshell, and how you take an abstract syntax tree and generate code from it, right? That we basically, on that last slide, showed you the code generation phase, where you take the abstract syntax tree and transform it into another programming language. But what about the parsing phase? You remember from that diagram, the parsing phase was the one that took that token stream and applied the rules of the language in order to determine whether it was a grammatically correct program and to turn it into its abstract syntax tree. What about that phase? So to do that phase, you have to write down what are the rules of the language. Like, let's say, and whenever you're developing a language, you kind of like always start small, right? So you may say, well, what are the rules for just writing down expressions? Expressions are any kind of like arithmetic calculations that you want to do. Like if I want to do 3 plus 4, what are some of the rules for that? Well, some of the rules I can think of here is if I want to add two numbers together, there's got to be a number and then an operator, which is the plus sign, and then another number, right? And I ought to be able to do it to like 72 plus 16. So numbers can be like more than one digit. And what about -6 plus 7? So here the numbers can be negative as well. So you really have to start thinking about what do my tokens look like? What do numbers look like? What do variables look like? Do I want to be able to do x plus 12? How about xy plus 36? Is that allowed? What about negative xy plus 36? Is that allowed? You know, these are all like little variations that you have to think about in order to really establish what are the rules for my language. And once you've figured those out, you can start writing down what those rules are. So right here, I've got a really simple set of expressions, but I can get more complex than that. What about 3 plus 2 times 6? What about 3 divided by 12 minus 8 plus 2, right? So the expression can start to get more complex. And so when you're writing down these rules, you have to think about, what do my tokens look like? And what are the rules for arranging those tokens into proper expressions? So here's what some tokens might look like. We have an identifier. So I'm basically defining what these tokens are. So an identifier is the letter A through Z. So it starts with a letter. And then after that first letter, it could have any number of additional letters. That's what the star here means. So this rule here says it starts with a letter, and then it can have any number of additional letters. Now, this is just the rule that I'm making for my language. Other programming languages have different sets of rules for what an identifier is. Like Java says it has to start with an underscore or a letter, and then it can have additional underscores, letters, or digits. And those letters could be uppercase or lowercase. And in fact, I think the very latest versions of Java also allow Unicode characters to some extent. So then you have to throw those in as well. What are the valid characters that I allow for my identifiers? So maybe for my purposes, I'll say identifiers are just lowercase like words, right? They have to be at least one letter long, but they can be any length from there forward, right? They can be 1, 2, 3, 100 characters long. And then finally, this semicolon just terminates this definition. So here's a definition that says I have an identifier that consists of a letter followed by any number of additional letters. And here's the end of the definition. And then I also have to establish what an integer looks like. Here I'm going to say an integer is, don't worry about this little pop-up here. An integer is a digit, 0 through 9, followed by any number of additional digits. Or it's a negative sign. So here I've put the negative sign inside of quotes, followed by one or more digits, and then the end of the definition. So an integer can take two forms. It can be just a series of numbers, a series of digits, or it can be a negative sign followed by a series of digits. And then I'll say, this is what an integer looks like for my programming language. And then another thing I might want to say is, what about white space? If I put spaces in my expressions, in my statements, does that count or not? Some programming languages, white spaces are mandatory, and some of them they're not. So I need to define a token for that. I'll make one called white space. And I'll say a white space can be, you know, a space or a new line character or a tab character. But I'll say, you know, in my language, white space characters, I'm just going to ignore those. So in this language definition, I'm going to say just any white space characters, just skip them. Don't worry about them. Okay, so now I've defined my tokens, and now I can start taking those tokens and putting together into larger things. So I can say an expression is something like plus or minus something else. Like I can go integer, and then it's, you know, plus or minus or times or divide. And maybe you can even put in or modulo, right? But you get to pick what the symbols are. That's the nice thing about building your own language. You get to pick those. We don't have to use the symbols plus and minus and slash and star. We could use something else. We get to decide what the language looks like. Okay, so we defined here that an expression is an integer followed by one of these 4 or 5 symbols followed by an integer, right? And then we can try it out. So I can go 3 plus 4, and then over here on the right-hand side, it has shown me what the abstract syntax tree is going to look like. Right? It's going to be an expression at the top with a 3 and a plus and a 4. And this 3 has been tagged as an integer. The plus doesn't have a, I didn't assign the plus a token, so it just says null here. But here's the plus, and then the 4 has been tagged as an integer, and then you combine that all together and you get yourself an expression. But if I type in something that's not an expression, like plus 3, 4, then it says, whoa, that's not correct. That doesn't make an expression because you can't have a plus preceded by nothing. And this end of file here, EOF means end of file. It encountered the end of the file before it expected something, before it expected one. But if I type in an expression that's too long, 3 plus 5 plus 6, you notice that my expressions here are only just a single integer followed by one of these operators followed by a single integer, and what I typed in is longer than that. So it only found the first one and then it just stopped. It just said, okay, that's enough. We got it. So how do we accommodate longer expressions? Well, we could write in another rule, right? We could say an expression is an integer followed by one of those 4 operators followed by an integer, or it's an integer followed by one of those 4 operators followed by an integer followed by one of those 4 operators followed by another integer. You know, and then we can accommodate longer expressions or shorter expressions. But then if we want to make them even longer, we have to write in another rule for that. So how do we accommodate expressions of just kind of like unlimited length? You know, 3 plus 4 times 5 divided by 6 times 8 plus 2 modulo 12. How do we do that? Well, that's where we need to make our rules recursive. If you'll say, you know what? An expression is just a tree, right? And a tree is a recursive data structure. So really, an expression is built up out of smaller expressions, and those expressions are built up out of even smaller expressions. And when we finally get to the leaves at the bottom of the tree, those are the smallest possible expressions we can have. In other words, an expression could be something like just the number 3. Right? In my calculator, if I just type 3 equals, it tells me the answer is 3. That's an expression. So I could say an expression is built up out of, you know, just an integer, or just an identifier, or it's built up out of an expression with those operations in them. And let me split this up onto different lines so it's easier to see. Okay, so we've got an expression is built up out of smaller expressions with these operations in between them. And so an expression can be either just an integer or just an identifier or two smaller expressions with an operator in between them. And so now we can put in like just 5. And actually, this is correct because it says, oh, it encountered the end of file. And I believe that will work. We can do 5 plus 4, and that works. We can do 5 plus 4 times 2. We can do 5, but if we throw in a character that doesn't know, then it can't build an expression out of that. So let's do 5 plus 4 times 3, and let's take a look at the tree we came up with. So we got 5 plus 4 right here, and then here's the 3 and the times. What if we put the times in front and then the plus on the back? Then we got 5 times 3, and then the 4 and the plus up here. Okay? So the question is like, what is this language? I'm just making up a language. Oh, by the way, this thing itself is a language. This is a programming language for building compilers. This is a compiler. So it's actually a program that takes in a language specification and will turn it into another program that we can then run and evaluate these expressions. Oh, and then the question also, what is this? What are these numbers here? This number basically means which rule are we applying. So this is expression rule number 1, expression rule number 2, and expression rule number 3. And so why didn't expression rule number 2 appear? Because we haven't thrown variables into our expressions yet. So let's put in like, age right here, whoops, plus age. And so now this is expression rule number 2, because expression rule number 2 uses identifiers. Oh yeah. So this is a tool called Antler, A-N-T-L-R, version number 4, Antler 4, and this is a plugin into the IntelliJ IDE, and allows me to write out these language specifications and then turn it into Java code, which we can then modify a little bit and turn it into a full-blown compiler. Okay, but the problem here with this is that all we said is that an expression is just another expression with any one of these 4 operations followed by another expression. In other words, it doesn't apply the order of operations. It doesn't put multiplication and division first and then addition and subtraction. It just simply goes left to right. So whichever expression comes first, that's the one it puts down towards the bottom of the tree. And whichever operation comes later, it puts it more towards the top of the tree. In fact, let's just make this a little bit longer. Let's go plus 4 times 5. And you can see it's really just building out this tree to the left. So we've got 3 times 5, and then we add age, and then we add 4 to it. And then we finally multiply by 5. There's no order of operations here. So in order to do that, we have to build a hierarchy into our language specification. And so we are going to do that by writing some additional rules. We'll say an expression is multiplication or division, or it's an expression that uses addition or subtraction followed by an expression. So by writing out these rules from top to bottom, whichever one it matches first is the one that will get built into the abstract syntax tree first. So we're putting our multiplication and division up towards the top because we want those to match first. And now let's take a look at our tree. So we got the 5 times 3 right here, which is this here. And then we've got the 4 times 5 over here. Okay? And then we have the plus and age from this multiply, and then the plus that adds the result of that left-hand expression to the right-hand expression. So we've now built into our language specification the order of operations. And, when we can build that even further, we can say, if we want to do exponents, we can do expression, let's say the caret for exponent. And then what went wrong here? We got plus and minus times divide. We have caret. I'm wondering why this is highlighted in red. I feel like I've just typed something. Oh, because it sees this -4 here and it goes, oh, that's a negative number there. Rather than a minus sign. So I'm trying to figure out, how do we get around that problem? How do we get around that problem of it thinking that this is not subtraction of a positive number, but it's actually just a negative number? I wonder if we put this rule first, and take this one out over here. Does that work? Nope. I'm not going to try to solve that problem right now. That's just something you have to figure out. I'm sure if I read the documentation for the Antler language, it would tell me what to do about that case, but I don't want to go look at that right now. So I'll just put in a plus. There. So what do we end up with here? So here's the age to the power of 6. And then that gets added to 5 times 3, and then that gets added to 4 times 5. Oh, it says one thing we could do is we just put spaces in there, right? Yeah, if you just put spaces around things, then it eliminates the ambiguity. That's good. Remember, we told it to skip white spaces, but in this case, the white spaces do help because it helps to separate the operators from the operands. Okay, so great. We've got something now that can take any expression that we type in and turn it into an abstract syntax tree to evaluate that expression. Now, this doesn't actually evaluate the expression. We would then have to go and write the code that would emit the assembly language instructions. But now that we have the syntax tree constructed, we could then go and say, let's see, where is it here? We go project, no, we go, here we go. We go project, source, and then we say generate the Antler recognizer. And then we look here, and down in here we've got expression, here we go, expression lexer. And this is the Java code that the Antler produced. So it wrote this Java code. I didn't write this, it wrote this. So based upon the programming, the language specification, it wrote this code for me. And down at the bottom, this is what represents the actual pattern recognizer. It looks like gobbledygook to us, but when this program runs, it actually goes through a character at a time, marking each one of the things that it finds, and it tags them as being integer or identifier or white space. And then we can also look at the parser, and its code looks pretty similar, but down at the bottom of it is the pattern recognizer for those different grammar rules, like what's an expression. So this is what's called a compiler. It takes it's a compiler that takes in this programming language and turns it into this programming language. So it compilers for you. And then you take this code, add a little bit to of your own stuff to actually, emit the target programming language, and then you compile that and turn it into a full-blown compiler. Right, it's a language for your language. It's a language specifier. Okay, so I'll show you one more thing in our little language here is what if we now want to do things like assignments. So we want to go like, x equals 4 plus 5. So we have to write down the rules for that. We might call that an assignment. And an assignment would look like an identifier, followed by an equal sign, followed by an expression. So let's type in a valid assignment. Let's go x equals 4. And that worked. We got x equals and then 4. X equals 4 plus 5. Here's our x, our equals, and then 4 plus 5. But notice we can't do anything like 4 equals x, right? That's not valid. That's not one of the rules that we wrote down. Age equals let's go like dog age equals age times 7, right? You take someone's age multiplied by 7, and that's how old they would be if they were a dog, right? So here is our expression that uses dog age as a variable and age as another variable, multiplies it by 7, and then assigns it. What we can't do is we can't go x plus 5 equals age times 9, right? That's not allowed because we can't put an expression over to the left-hand side of an equal sign. Okay, now the next question would be, what if we want to have more than just an assignment? What if we want to do 2 assignments? What if we want to say like x equals 5 and then y equals 12? Well, now we need to have some kind of statement separator. In languages that you've probably written in, like Java and C and C++, you use a semicolon as the statement terminator. It says the statement is now done. In Python, the statement terminator is the enter key. But in our language, we said the white space doesn't matter. Just throw those away. So that's why we have to use something like a semicolon to indicate the end of a statement. So we can say here that a statement is an assignment followed by a semicolon. So now we have to put on the semicolon. It's now mandatory. If we leave it off, we get an error. But then this doesn't allow us to do more than one, right? Because we only said that a statement is just a single assignment. So then what we can say is a statement consists of an assignment followed by a semicolon, followed by any number of additional assignments. So we've got a statement is an assignment followed by a semicolon, followed by any number of additional assignments. And in fact, we could go a little bit further than that. We could say a program consists of a statement followed by any number of additional statements. I like that one better, because then we can say a statement is just a single assignment, but a program consists of one or more statements. So we got one single abstract syntax tree that consists of two statements. The first statement is an assignment. The second statement is also an assignment. And then what if we want to put like, let's say we could put in like an if into our statement, into our program. So we could say a statement is an assignment followed by a semicolon, or it's a conditional. Let's see. Yeah. And so a conditional is the word if, followed by a parentheses, followed by an expression, right? It has to be, like, x is greater than 5 or something like that. Followed by a closing parentheses, followed by maybe a brace, followed by, well, what goes inside the braces? Well, statements go inside the braces, right? How many statements can we have? We can have as many statements as we want. We can put one thing in there, we can put many things in there. And we already have a rule for that. A program is one or more statements. So inside the braces goes a whole program. All right, so let's try that out. If x, y equals 5. And remember, white space doesn't matter, so I can put some indentation there. So I have program, statement, conditional. Here's if, open parentheses, x, close parentheses, open brace. Here's a statement, which is an assignment, y equals 5, and then the closing brace. What if I want to do greater than or less than? Well, I got to put that into my expressions down here. I got to add those operators. But what this allows me to do now is that inside of my conditionals, I can put more conditionals. Uh-oh, some kind of error here. Oh, I think it worked. So remember, inside of the braces, I'm able to put a complete program. And a complete program consists of other statements. And those statements can be other conditionals. So already here, I've got the ability to build nested conditionals without really adding anything else to my grammar here. I just said that inside the braces goes other programs, and then it just works. So this is what allows you to build programs of unlimited complexity in whatever language you choose, Python, Java, whatever it is, C, C++, because a program language is defined recursively. Inside of any one of those braces can go additional small little programs with some restrictions. Inside of conditionals can go other conditionals. Inside of expressions are other expressions. And so with a fairly small number of grammar rules, you can build programs of unlimited complexity. And that's really cool, I think. And you're right, as in this little programming language that I wrote, I only have one type. I just have integers. But I could go on and define other types. I could define what a floating point number looks like. I could define what strings look like. I could define what arrays look like. If I wanted to directly support arrays, let's say with bracket notation, I could define what that looks like. So again, all this does, it just defines the grammar for the language. Does the program follow the rules of the language? This does not have anything to do with the semantic analysis, which is, does the program make sense?
Do you also define size limits here as well? So like, let's say if you were doing a floating point number, would you also decide how big of a number you could input in there? Like how many bytes that floating point number can take up?
That'd probably be in the semantic analysis phase.
Okay.
So the grammar would be, I could type in a floating point number of like arbitrary size, like hundreds of digits long. But the semantic analysis would go, oh, actually that's too big to fit inside of a float, so it's not going to work. Same thing with things like integers. I could type in one that's as long as I wanted, but the semantic analysis phase would go, that's not actually going to fit in 32 bits, so we won't allow it. So that's a little bit about how programming languages are defined. And you also got a little bit of a taste for how the pattern matching is done. So as we move into the next few weeks and we start learning about regular expressions and finite state machines, we're going to see this pattern matching syntax come up again. The vertical bar meaning or, and the star meaning repetition, and the brackets meaning sets of characters. We're going to see those come up again. If you've taken like the Linux or Unix courses and you're familiar with commands like grep and awk and sed that are used that use pattern matching, you've seen those characters before. And so it's really cool, I think, how all this stuff kind of ties together. Regular expressions, data structures, trees, traversals, all the stuff comes together in order to make what we sort of take for granted as beginning programmers, the compiler. So the comment was, the only limit is hardware. And we've already seen examples where there are some programming languages that don't try to limit you by the hardware. Python is one of them. Right? Underlying your Python program is a 32-bit or a 64-bit machine that can hold integers up to only a certain size, but it tries to hide that from you and make you able to use integers of unlimited size. There's going to be a little performance penalty when you do that, but it's not really your concern as a programmer. If you want to make your code run as fast as possible, sure, you'd be concerned about that. But by allowing you to use integers of arbitrary size, it frees you up from thinking about, is this going to fit inside of a 32-bit number or 64-bit number? And you can write programs that don't have that limitation. And so that's really kind of the purpose of a virtual machine in the Java sense or the Python sense, is that it abstracts away the limitations of the hardware and gives you essentially a new piece of hardware that doesn't have some of those limitations. The Java virtual machine hides from you like how much memory your computer has, and it makes you think that you have almost an unlimited amount of memory. and it hides from you the fact that there's underlying representations for integers and floats. The language specification says a float shall be a 32-bit quantity. But if your architecture doesn't have 32-bit floats, then an implementation of the JVM for that architecture ought to simulate them so that you believe that you do have those things. Dynamic array allocation, dynamic memory allocation is not a feature of the hardware. Right? Most processors don't know how to allocate memory. They just make available the memory that you do have. And so you have to layer on top of that an abstraction that says I can allocate as much memory as I need, even though my actual hardware may not have that amount of memory. I've got little computers like, I'm looking over here on my bookshelf to see if I have one handy. I got like the Raspberry Pi, little tiny Linux-based computers that might only have a gigabyte of memory or less, half a gigabyte. But I can allocate more than a gigabyte of memory to my program because it has this concept of virtual memory that makes your programs believe that there's more memory than you actually have. So that's really one of the purposes of operating systems, is to layer on this abstraction of the machine so that your programs don't have to concern themselves with the actual underlying limitations of the hardware. And that's the same thing that programming languages do, is they abstract away the hardware itself and present to you a machine that doesn't have some of those limitations. It might have other limitations, but it may not have certain ones.
With the virtual memory, so you would still have the memory limitation, but you wouldn't, like, it would only come up if you were to use the 1 gig or however many, however much size you have. Or is it just a memory limitation that it like puts unused memory into like hard disk storage?
Yeah, that's one of the things that virtual memory does, is that any memory you allocate beyond your physical limitation gets shunted off to the disk drive. And so it's using the disk as an extension of memory. But the other thing virtual memory does is it presents to you, let's say, a memory model that has 4 gigabytes of available memory, even though your hardware may only have 1. So it makes your program think that there's more memory available than there actually is. And one of the ways it does it is by paging memory off to disk. Does that make sense?
That makes sense.
So it's kind of like you have 1 gigabyte of physical memory and 3 gigabytes of virtual memory that's sitting on the disk for a total of 4.
I've heard like there's some processors that use like, let's say, I don't know, the GTX 970 from NVIDIA a long time ago. It had 4 gigs of memory of VRAM, but in real world cases, you would only be using like 3.5, and then that last 0.5 of a gig would be slower memory. And is that kind of like an application of virtual memory or no?
I could see that, although in reality, it might not work that well because moving data to and from the graphics card is pretty slow, relatively speaking. But I could see someone maybe using the memory on a graphics card as an extension of system memory. But it's probably, I don't know, disk drives and storage devices are ubiquitous, right? Every computer has them. Not every computer has the graphics card, so I could see that'd be a pretty specialized application. But it could be done. I don't see why not. Yeah, so if you're looking at a comment here, so if your application uses more memory than is available, then it starts using the disk drive, and that's really slow, really slow. And then your application gets, as you said, kind of laggy and glitchy. So you do want to have as much physical memory as you can in order to avoid using the disk drive. You use a disk drive as a kind of an overflow. It's where you can put memory that isn't currently being used. Like if you have 2 applications open, you got your web browser and you have your IDE open and you're not currently using your web browser, then the operating system may elect to take that memory and move it out to the disk drive in order to free up more for your compiler. And then when you stop using the compiler and use your web browser, then it flops things around. It takes the virtual memory for the web browser and moves it into physical memory, and takes the stuff for your IDE and moves it out to disk. So just because it's using the disk doesn't mean that things are going slower or a lot slower. It just means that the operating system is managing those resources for you, and in some cases it can manage it well enough that you don't really notice that this is happening. Yeah, so good management of caches and virtual memory can make it so that you have a lot more memory available for your programs, but you don't even notice that this is happening behind the scenes because it's timing those page ins and page outs to the point where they happen during times of your program that it's not, what am I trying to say here? Like let's say you have a program that does computations and then waits for user input, right? So it could do some of that memory moving while you're waiting for input so that you don't really notice that memory is being swapped in and out. If you do it during the computationally intensive part of your program, then you'll see that things are lagging because it has to stop and wait for data to be moved out to disk. But if you do it when you would normally be just sitting there doing nothing, then you might not notice at all that anything is happening. Like on my Mac right now, I've got 16 gigabytes of physical memory, of which 15.5 is being used, right? But that doesn't mean that my applications are using all 15.5. It just means that it has filled up the remaining free space with things like files and frequently accessed documents on my disk, like icons and graphics. Those get pulled into physical memory in order to make them quick to access. But my virtual size is, let's see if I can find that information here. I should use a different program that will tell me. Oh, it says out of my memory, I'm using 5 gigabytes out of 16 gigabytes of memory, but almost all of it's filled with other stuff. Right? My programs are actually only occupying this green section here, but things like my files and frequently accessed documents are this yellow section here. And then my swap space is 147 megabytes out of 1 gigabyte. So it really hasn't allocated very much for swap space yet. But it's still using some. So programs that I'm not currently using get swapped out to disk. And then when I switch to them, it'll quickly move them back into physical memory, and I might not even notice that ever happened. All right. Well, that's what I wanted to cover for today, was just a brief overview of how compilers work and how some of these data structures like trees fit in to kind of the overall picture. And then we'll start digging a little bit deeper over the next few weeks into how do these things like state machines and pattern matching, how does that work? And again, it uses specialized kinds of graphs and then algorithms that operate on those. Does paging out to memory hurt the hard drive? For a traditional hard drive, like a spinning one, not really. I mean, because the magnetic platters on them can be written to and read from almost an infinite number of times, but they are really slow. On modern computers, you probably use an SSD. Those do have a limited lifetime on them. Each cell of an SSD can maybe be read from and written to, like 10 million times or so, 100, I don't know what the number is, million times, 10 million times. And so the SSD controller's job is to make sure that no one cell gets like a whole lot of activity. If it notices that things are being written to one cell, it'll temporarily move that cell to a different location on the SSD so that that one gets written to. And so it'll spread the load across all these flash memory chips to ensure that none of them gets written to a whole lot. And so that spreads the load out and extends the lifetime of the SSD. But as one of those cells approaches its lifetime, the controller will then lock out that cell and it can no longer be written to. And then essentially the capacity of your SSD just got a little bit smaller. So over time, the capacity of an SSD gets smaller and smaller as the cells wear out. It still takes a really long time for that to happen. You know, you're more likely to upgrade your laptop or your computer before that happens. But on things like servers in data centers, that is a concern. And so they actually use different kinds of SSDs that have longer lifetimes on them. Okay, well, I think we've reached the end of today. We'll be back on Wednesday, and we'll start talking more about state machines and pattern matching. And then we'll be doing that for a couple of weeks. And then that'll finish out the semester, along with about a week of extra stuff towards the end. Well, I hope you all have a great day. Enjoy the weather where you are. It's sunny here today, but it's going to be raining tomorrow. Okay, we get some rain. It's good. But I hope wherever you are, it's great weather, and you get some rest, get some programming practice, and I will talk to you later. Take care, everyone. Bye-bye. All right, and the YouTube folks, it was good to see you today. Yep, we took a week off, and now we're all back. And so I think there's no more holidays for the rest of the semester. So it's going to be every Monday and Wednesday from here on out till about mid-May. And then also on Tuesday and Thursdays, I have my C programming course, and we're going to continue writing programs to crack passwords faster and faster by building a data structure. And then we'll move into computer networking. So you'll want to check that out on Tuesdays and Thursdays. Same time, 9:30 Pacific time. You want to know how to do Python for abstract syntax trees? So I believe Antler can output not only Java, but can also output Python. But how would you do a tree like by hand in Python? I would probably do it by using the object-oriented features of Python, where you can build a class that represents a node, and then you could build methods for that. I mean, all you really have to do is just define the data structures for any kind of tree, or a binary tree, or actually any kind of tree, and then just build your abstraction syntax tree out of that. So I mean, if you know how trees are built in a programming language, it's not that difficult. Now, if you don't know how trees are built in a programming language, then that kind of like opens up a whole like discussion we could have for hours and hours about how to do that. And maybe there's already a library out there for building trees in Python, but it's not that much difficult, and not that much different from doing it in Java. In Java, you define a class that represents a node can have a value along with some children, and then you just build your data structure out of those. And you probably want to have some methods for doing traversals in order, pre-order, and post-order. Things like the Antler programming environment or the Antler library does a lot of that stuff for you. In the code that it generates, there are methods you can call for doing those traversals. So what you end up doing in your program definition here, your language definition, is you say something like, if you encounter, let's say, this, then you'll emit, like you'll say like system.out.println, load or I should say, add the first thing and the second thing. So the dollar, I'm kind of making this up as I go here, but this is basically the idea. So you'll say, if you encounter this rule, then you'll execute this little piece of Java code. And this little piece of Java code just simply prints out some assembly language instructions where the $1 and $2 represent the expressions that were matched over here. And where you put this code can either be here, or it could be here, or it could even be like in here. Oh, I meant like in here. So where you put that code turns it either into a post order, an in order, or a pre-order traversal. So here I've got the code afterwards, so it becomes a post order. If I wanted to do a pre-order, I put it in front. And if I want to do it in order, I put it right here in this stuff over here. So when I run this Java code, I'll call the tokenizer or the lexer, and then I'll call the parser, and then what gets returned to me is the abstract syntax tree, and then I call a method on that just says walk the tree, and then as I walk the tree, the code is the compiler code is executing this little snippets of Java code as it encounters each one of those rules, and then all this my program turns into basically is just a whole series of print statements, and it just outputs my assembly language code. It's kind of hard to describe in a nutshell what's going on here. That's why there's a whole book written for it. Well, that's strange there. Oh, there we go. I mean, if you can get a hold of this book, the Definitive Antler 4 reference, and I believe there's actually an online version of this book. You don't have to buy the book. I think there's an online version of it that you can get for free. But it basically walks you through the whole process of creating a compiler from start to finish and teaches you all the concepts along the way. It's really great. So you can get the reference documentation. Yeah, getting started, grammar structures, parser rules, parse trees. That's the abstract syntax tree I'm talking about here. But if you can, get a hold of the book. The book is really great because, again, it teaches you not only how to use Antler, but also goes over all the terminology, all the concepts about how to build a compiler from scratch. It's really fantastic stuff. When you discovered that there is a Python abstract syntax tree module that could work with that. So I mean, maybe what you're talking about is there is a module built into the Python language that gets you access to the underlying data structure for your Python program itself. So you can type in a Python program and then execute it, and your Python program could like stop in the middle of it and analyze the data structure and make changes to it. Like the code can actually rewrite itself if it has to. And I was going to do that. This is one of my sort of ongoing projects is if you followed along with the Python notebook assignments, you saw in the middle there were like these asserts, right? Assert that a call to this function produces this value. And sometimes the error message that it produced was really not that easy to understand, because really it's producing an error message for that Computer Science 26 library that I wrote. And what you're seeing is the error message generated by that code, not by the code that you wrote. And so what I wanted to do was write my own, essentially, assertion library. I would change the name of the method to like check or something like that. Check that this function call produces this result. And if it didn't, it would though go and then walk your abstract syntax tree of the function that you wrote and try to identify where the problem was. You know, types didn't match up, or the array wasn't the right length. And so it would look at the abstract syntax tree for your Python program and attempt to analyze it and figure out where the problem lies in your program, not in the code that I wrote, and not in the Python interpreter. And hopefully give you better error messages than the one that Python produces. Python's error messages are not that great, honestly. I've seen better error messages out of C compilers than Python's error messages. So that's sort of like one of my ongoing projects, but I have not made a whole lot of progress on that. Yeah, wouldn't that be great if you're a beginning programmer and the compiler produced really outstanding error messages for a subset of the language. So let's say you're learning a language and all you know, let's say you're learning Java, and all you know how to do is write a simple class, and you can write like your main method, and then you just do like print statements and calculations. And that's all you know so far. That's like week number 1. So you could have a Java compiler that understands that this is the kind of program you're going to be writing. It doesn't involve classes or enums or interfaces. It doesn't use objects. It doesn't use anything beyond just like printing things out, simple variables, and a main method. And it produced error messages for that subset of the language, like just for that subset. So anything else you tried, anything you tried with arrays, anything you tried with conditionals, like it just says that's not allowed, right? And it produced really great error message for that subset. And then once you're beyond that first week, you then move on to like second week, in which you can do conditionals and you can do loops, and maybe you can define your own methods now. And so it understood that language and can produce error messages for that, right? And so it's kind of like this tiered, layered language that grows as your maturity in the language grows and produces error messages that are particular for you. And so I think that's a really great educational tool. And I know there are some people that are working on exactly that, of a Java compiler that grows as you grow and produces error messages that are suitable for your level of maturity. Because right now, Java's error messages assume that you're like an experienced programmer that's been doing this stuff for years and years, and it produces error messages that an advanced person can understand, but that a beginner finds just totally incomprehensible. Right, so maybe in, like someone here said, like maybe in a first tier of the language, you don't allow, like you require braces around a conditional body, right? You require them. In Java, the language itself, if they're not required, if you only have one thing to do, you don't have to put the braces on. But maybe for a beginner, you say those braces are required, even if you only have one thing to do. So the compiler could check for that. Oh, you're missing those braces, put them in. Later on, you can relax that rule and say, okay, we'll allow you to do conditional bodies with no braces, but for a beginner, you have to put them in. Maybe the beginning version of the language could disallow empty loop bodies. Like you have to put something inside the braces. Currently, you don't. You don't have to put anything inside the braces. But it might save you a lot of time if it flagged that thing, if it flagged those kinds of errors. Anyway, so that's something to think about. Well, like I said, I hope you have a great day, and it was good hearing from all of you and seeing all of you again, and we'll be back on Wednesday. So take care, get some rest, do some programming, have fun, and I'll see you later. Bye-bye.